చెప్తాను, ఒక 2 seconds ఉండండి. థ్యాంక్ యూ. వస్తుంది మేడం.
వస్తున్నదా? ఓకే, థ్యాంక్ యూ.
వస్తుంది.
Okay, apparently I'm online, but I can't see myself on YouTube, so we'll just take it on trust. Good morning. We'll continue with general histology. Now, many of you have been asking me separately, privately, about the portion and the date of the part completion test or the formative evaluation. That will be put up by the vice principal. So each department has given him the portion, and the college will be announcing that on your website. So don't worry about it, there's still time. You just concentrate on understanding and getting updated with all your lessons. Alright, I still can't see myself online, but I'll assume that it's coming. So we'll hope that I'm beaming online. We'll start, or we will continue rather, because I have mentioned lymphoid tissue before. We'll look at it in a little more detail. I found a very nice PPT online, the author of which is Major Dr. Rishi Pokhrel from the Nepal. He's a member of the Nepal Army Institute of Health Sciences, and he's put together a very good slideshow, but there's a lot of theory. I won't be diving into that. I just wanted to show you the pictures, because so far I've shown you extremely high power photographs of the microscopic view to be able to explain the subcellular components in more detail, which anyway you'll get from your theory books. But I also want you to start getting an idea of what a slide actually looks like under hematoxylin and eosin stain. So I'll do that now with lymphoid tissue, and over by this month, over the month of April, we'll look at other tissues also, the actual slides, what they will look like, because that will help you to anchor your learning. Even if you've not seen the slides yourself, it will help you to set a practical context for the theoretical learning. So, alright, let's get on with it. We have already mentioned there was a lymphoreticular system or a hemolymphoid system. Now, different countries, different textbooks classify it differently, but the moot point is not whether we should call it this or call it that, but that we should understand how it all fits together. So normally we draw lymphatic tissue, either the organs such as lymph nodes or tonsils or spleen or thymus in green, and the lymphatic channels, particularly lymphatic capillaries, which are a different set from venous capillaries. Now in the blood vascular system we had mentioned that the vessels, the network of closed vessels which together make up the circulatory system, is one to which the heart is connected with incoming and outgoing tubes, so that whenever the heart pumps, that pressure is communicated through the whole arterial tree and returns back to the heart through lesser and lesser pressure systems, and keeps going because of the functioning of this muscular pump. But the tree network is of an arterial big vessels with smaller branches and smaller, and then they get into the finest division of branches which are called venous capillaries, right? Now those venous capillaries reconstitute back, join, some of them will join back and form a venule, several of which will join and form a vein, and several small veins will join up and form a large vein, and then the large veins will return the blood to the heart. Now that was the system there. There is an exactly parallel but completely different system of even finer capillaries, they're even thinner if it's possible. In the blood, RBCs are about 7 microns in size. So the width or the diameter of a venous capillary channel has to be at least 8 microns to allow RBCs to get through it, to pass through it in single file, one behind the other, allowing maximum exposure of their circumference and their surface area for exchange of oxyhemoglobin, carboxyhemoglobin, right? That is what has to take place. Plus also for exchange of nutrients from the plasma. So all the nutrients will be taken away by the tissue through which the capillaries are flowing, and the waste products from the tissue cells will be thrown into this plasma again. So plus there's a lot of ionic exchange, a lot of stuff is going on between the blood and its the tissues that it is feeding. Lymphatic capillaries have to do only, or have to deal only with the WBC component of all of blood, right? Nothing except the WBCs and a little bit of extracellular fluid comes through into the liquid that we call lymph. So lymph channels by their nature can be even thinner, finer than the venous channels, because firstly RBCs are not going through and they don't have to be limited within the lymph channels. Secondly, WBCs have this extraordinary function called diapedesis. They're able to squeeze through in between gaps of their containing vessels, and they're able to get out of the vessels easily, and they're able to enter the vessels easily. So the traffic between a lymphatic distributary system and the tissue that it is serving is cellular. Cells themselves leave and cells themselves come back into the lymphatic channels, whereas the traffic in the blood vascular system is mostly molecular and ionic. Cells in general don't leave. RBCs don't leave at all. Platelets will rush out only if there's a gap or a break in the capillary. Otherwise they stay within the plasma. WBCs, like in lymph, can also move in and out, but the series of WBCs which move in and out of blood venous capillaries, they are not so active. They're capable of it, they do it also, but they're not so very active. We'll see that in a little while. But the point is that lymphatic capillaries are finer, thinner, and their network is such, you see this green one, that they don't have their own pump. So how do we keep the lymph flowing, right? It's a very pale milky white fluid, not even milky actually, until the lymph from the digestive tract is entering into it, because the lymph from the digestive tract will bring in the fat micelles, the fat component of your 6 classes of food. Only the fat component will be absorbed into the lymph vessels of the digestive tract, and those micelles, MICELLES, those little droplets of fat which are absorbed. If you look at with the naked eye, if you look at lymph, it gives it a milky white color, which is why the lymphatics of the digestive tract are called lacteals. Looks as if they're carrying milk. But only for the digestive tract. Lymph anywhere else, WBCs in lymph anywhere else are colorless. They don't give any color to lymph. And since there are no RBCs in it, it's not red or blue or anything. There's no oxyhemoglobin or carboxyhemoglobin to deal with. So to the naked eye, the appearance of lymph is colorless, like water, except the lymph from the digestive tract. So when that digestive tract lymph mixes up with all of the lymph, it is slightly turbid looking, slightly like coconut water, or a very, very slightly opaque white color fluid, which is going to be there in this whole network of capillary branches, which will join up and form lymphatic channels, which will become bigger and bigger and all become tributaries to one central duct called the thoracic duct. And this keeps getting flowing proximally. From the tips of your toes, lymph will flow proximally. It will get interceded or filtered by a bunch of lymph nodes behind your knee joint, then flow proximally, get filtered by another bunch of inguinal nodes at your groin or inguinal region, then again flow proximally, and finally join up with this thoracic duct system. Similarly, lymphatic vessels of your digestive tract. Similarly, lymphatic vessels of upper limb and head and neck and everywhere else. So what we see is that these lymphatic channels will be interceded or interrupted by these groups of little lymphoid organs, and succeeding levels of filtration of the contents of lymph will happen by this lymphatic organ. But there is still no pump. So this lymph has to come back and return to the heart in such a way that when the heart pumps, then the blood fluid, plasma, which goes out into the most peripheral of your tissues, much of it will come back via venous capillaries, but a small quantity of that extracellular fluid which flows out in between the cells of your tissues will return via the lymphatic capillaries. Okay. In physiology, they'll talk about the pressure gradients and all that. We just need to know that there is a whole bunch of organs associated with this system. In the neck region, we have the tonsils. In the chest region, we have the thymus. In the joints of your limbs with your torso, it means axillary region as well as hip region, we have larger groups of very prominent lymph nodes. So we have lymphatic vessels throughout. The liver is an important lymphoreticular organ. The spleen is one organ. There are underneath the epithelium lining of the small intestine, there are aggregates of lymphoid tissue which are called Peyer's patches. They are one important organ. The appendix in the digestive tract is considered to be an important lymphoid organ, and bone marrow is where the three classes of blood cells are anyway being produced. In some ways, that also makes it a lymphoid organ. So, lymphatic system consists of mostly extracellular fluid, tissue fluid, with a whole bunch of WBC derived components in it. So you can say it's a variety of connective tissue consisting of the liquid called lymph, network of vessels, nodes and nodules. MALT, I have already mentioned in a class before, is mucosa associated lymphoid tissue, tonsil, spleen, thymus and bone marrow. These cells and all you will do in great detail in physiology. What we need to know is that any one lymph node, which is the ovoid little thing, has incoming lymph vessels and outgoing lymph vessels. So the incoming ones are called afferent. They join at the periphery. They come and join the lymph node, a whole lot of them, at the periphery, and WBCs will flow through, and some filtration will happen while it is passing through the node, and then the efferent lymphatic vessels will be carrying cleaner lymph. Any infectious organisms, any foreign proteins, any cell debris, all the rubbish that you don't need will get filtered off there, and cleaner lymph with healthier bunch of WBCs will flow out. And eventually, from every lymph node, if you take the efferents of all the lymph node filtrations, they have to come back to the blood vascular system. So they join the right lymphatic trunk or the thoracic duct, which I mentioned earlier, and they join back the big veins which enter into the heart. Okay, this is the plan that you have to remember. The second thing you have to remember is that there is something called a high endothelial venule, which is there inside of the lymph. Now, how did that come? Because every lymph node will have its own blood supply. It has to be kept alive, right? It needs arterial blood, and it will give away venous blood, which will be branches from the arterial system. There it will break up into a capillary network like any other tissue. Then that capillaries will get reconstituted into the venules serving the lymph node, but the difference is they have a high endothelium. We studied when we did epithelium that simple squamous epithelium is the classical type of epithelium which lines the blood vessels, all blood vessels, including the endocardium of the heart, right, is a single sheet of very, very, very flat cells, simple squamous epithelium. So whether it's a lining of a venule or a artery or a heart or a capillary, that is only one type of lining, which is called tunica intima, and in that there is only simple squamous epithelium. But in the lymphoid tissue, it seems to have, on the venule side, when venules are being formed from the coming together of several capillaries, they have high endothelium. See, the endothelium is looking more cuboid, it's not looking flat, right? There is a functional component to it, and WBCs are able to squeeze out and get out into the lymphoid tissue space, where modification of it will happen depending on whether it's healthy or not, or whatever else is happening over there. So that's one histological point, extra point for lymph node. So the drainage area of that thoracic duct which was centrally running, that green channel, is the whole body except the right side of the head and neck and upper lip. So this area is drained by a exactly parallel mirror image, right side, right lymphatic duct. Just take it, and then when we do dissection, you see the thoracic duct in the chest, you'll get a better idea. This is not important from histology point of view, just to know that there are two large lymphatic channels which will become tributaries to the vena cava, which will return the blood to the heart. So we classify lymphoid organs into central and peripheral. In center we have the thymus, which I said is in the chest, and the bone marrow, which is there in the central canal of all the long bones, and also in the thin slab of tissue in the flat bones, such as in the cranial vault, flat bones of your skull, in the sternum, which is a flat bone, in the iliac crest, which is a flat bone. So the bone marrow is considered a central lymphoid organ, whereas lymph nodes, spleen, mucosa associated lymphoid tissue, and gut associated lymphoid tissue are all considered peripheral lymphoid organs. Another way to classify them would be discrete lymphoid organs, which can be seen separately like different things which have a location and a margin, or diffuse lymphoid tissue, which is actually the larger quantum of lymphoid tissue, is in the form of Peyer's patches and bone marrow. So lymph nodes, spleen, thymus, tonsil are the four discrete tissues which we discrete lymphoid organs that we know, and we will look at them under the microscope. So they protect against foreign material. They are where the clonal production of lymphocytes and macrophages happens. It assists in circulation of body fluids by pressure and volume of ECF, and it transports dietary fats, which I already mentioned. So the thymus is in the chest. We won't look at the gross anatomy. In histology, the thymus is composed of lymphatic tissue subdivided into lobules. The immature T cells, which originate in bone marrow, they migrate to the thymus long back, very, very, very early in your life. And there they develop into what we call mature T cells, T for thymus. From there they are released into circulation. Also, there are other molecules in the thymus called thymic hormones, which help this maturation. So when you look at the slide of thymus, you'll see that on the outside there'll be a connective tissue domain, which is pinkish. It's consisting of fibers, which is just laid down there, holding the whole organ together. And on the surface, you'll have some cut sections of blood vessels. This connective tissue layer will be sending in branches, trabeculae or septae, which divide the whole area into discrete areas, which are going to be called thymic nodules. In each of these nodules, there will be a dark peripheral area, and there will be a lighter central area. So the dark peripheral area for each of these nodules is called its cortex, and the light central area is called the medulla. But when you look at the whole thymus as such, it's not as if there are separate nodules with separate medulla. If you look at it, the single medulla, which is there in the center of the thymus, is branching and becoming the center of each of the peripheral nodules. The way I like to describe it is like grapes. If you take off the grapes, you have a tree which has branches going into the center of each grape. So that's how the medulla operates within this lymphoid tissue, and it's not visible like that, but you may or may not see the connectedness of the medulla unless you have it in a certain kind of section. You will probably see this kind of magnification under the microscope, where we will focus for you a bit of capsule with a septa or trabecula going in, and a closed section of a lymphoid nodule, which shows densely purple staining circular dots, and suddenly that darkness becomes little lighter in color, where the purple staining has become lighter, more pinkish purple, and the dots have become little separated, loosely arranged, not tightly packed but loosely arranged. And in that medullary area of this one particular thymic nodule, you'll see certain larger circular pink structures which look like a onion peel, like having concentric circles of pink, like the layers of an onion, and they are called thymic corpuscles. And if you see a thymic a corpuscular structure inside the medulla of a lymphoid organ, then that has to be thymus. It can't be anything else. That is the way we recognize thymus compared to any other lymphoid organ. Firstly, all lymphoid organs will have dense aggregations of lymphocytes which will stain very dark purple. Lymphocytes are a large nucleus surrounded by a thin rim of cytoplasm. So at low magnification, you get to see only purple dots, nothing else, only as if it's a few 100,000 lymphocytes together. Densely packed is the cortex, loosely packed is the medulla. Inside the medulla, you'll see blood vessels and fine channels, but if you see pink layered circular ovoid structures, then they are corpuscles or thymic corpuscles or Hassel's corpuscles, Hassals, named by Dr. Hassel. And that is why that appearance of that structure inside the medulla will be typically of a thymus. I won't go into this is all theory, and until you see the thymus in the chest, I don't even want to talk about this. But a difference or a misdevelopment or a mistake or a disease of the thymus can lead to certain syndromes which you may have heard about. De-Georges syndrome is there's absence, a baby is born without a thymus and without the parathyroid, and there'll be a defect in the cardiac outflow tract. So it's very difficult. It's very difficult to be compatible with life. Children don't live very long, but these are rare. Myasthenia gravis is a developmental disorder. I think Amitabh Bachchan made it famous because at some point he was diagnosed with this. So you can do that as an interesting homework. But the point to remember is that the thymus is a lymphoid organ and is characterized by this lymphoid or lymphatic nodular picture with cortex and medulla, with capsule and trabecula, afferent incoming blood vessels on the periphery. And when you look at the medulla a little more carefully and at a slightly higher magnification, you get to see typical pink layered circular ovoid structures which we call thymic corpuscles. Lymph node is another kind of discrete lymphoid organ. So this is the lymph node taken out at surgery, hardly about 2 centimeters. Nothing very fancy about it. This is a diagrammatic view. When you cut a lymph node, you see that you have incoming vessels. You will have one area which is called the hilum of the lymph node. So it's like a kidney bean shaped structure. The convex side is where the afferent lymphatic channels are coming in. The concavity, the hilum area, is where the efferent vessels are going to go out, both its artery and venu as well as its lymphatic efferent capillaries. And inside of it is going to have again lymphoid nodular structure. So any one small lymph node, the whole node has one single cortex and one single medulla, right? So medulla is the area which is lighter staining, where the lymphocytes are more loosely arranged and not in nodules. Here can you see in the cortex the lymphoid tissue is always arranged in a nodule, an ovoid or circular area with a dense staining periphery and a lightly staining center. So this whole thing would be the cortex of the nodule, right? But we don't call it cortex and medulla for the lymph node. The cortex is where the entire bunch of nodules is there. See, cortex. Cortex is from the outside connective tissue, which is the capsule of the lymph node, to as much as being occupied by the dark stained areas, and the light stained area in the center is where a lot of blood vessels will be seen. H is for hilum. This is supposed to be H, not I. So the vessels which are going to be formed here will exit from this point and leave the lymph node. So we have a cortex, medulla and hilum. This is a single view. You're looking at the whole lymph node section in one view. We may not see that in the exam. What you will see, let me see, I don't think I have another picture. Alright, we'll make do with this. So we will focus a section something this much, right? So that you will see cortical nodules and you may or may not see the medulla. But the thing to remember is, it's not labeled in this particular diagram, that under the capsule, I don't know if some areas you can see, right under there is a capsule, there's a connective tissue domain outside. Between the capsule and the beginning of the lymph nodules, there'll be a little gap, a very, very thin white gap, which is called the subcapsular lymph sinus. So that is the one which will help you to identify the lymph node. Otherwise, basically, when you look at so much of purple with a darker outside and a lighter center, you know it is a lymphoid organ. In that lymphoid organ, when you look at the capsular area, if you're seeing a subcapsular lymph sinus, it is a lymph node. Plus, it won't have Hassel's corpuscles, it won't have the other features of the other organs. So what it basically will look like is a subcapsular area where some amount of lymphatic fluid will flow. Then it will filter through these nodules, come to the medulla, and then it will come out as a efferent lymphatic vessel. That's the architecture, that's the plan, that's the geometry, right? So you have incoming vessels. Can you see they've all got valves? The cut sections of the vessels show valves. So lymph always flows in one direction, from the most peripheral part, tips, fingertips, toe tips, nose tip of your scalp, from all the your periphery towards the center, and the lymph will only be able to flow from in one direction, won't be able to return back. And as it goes more and more central, once it empties in the blood, the pumping action takes place and redistributes the lymph. Okay, so we have a capsule, we have a subcapsular lymph sinus, we have afferent lymphatic vessels you may or may not be able to see. We have trabecula, which are extensions of the capsule which divide the cortex into further areas. Each of the lymphoid nodules has a germinal center. Now this light central area for each nodule is called a germinal center. That's a correct name, and that's what we name it in lymph node, in spleen, and in tonsil. But when you look at it in thymus, what we saw, we call it medulla straight, because that center was shared by all the nodules. It's a continuity. Whereas in the other three lymphoid organs, it is separate. The germinal center of one lymphatic nodule is only its own center. It is not connected with anything else. And the whole organ together has a medulla. Right? The whole of spleen will have a cortex and it will have a medulla. The whole of tonsil will have that. But only in thymus, you will have the medulla of the whole thymus appearing in the center of each of the nodules of the thymus. Okay, just remember that as a concept difference between thymus and the other three. Okay, we saw this picture earlier. So the lymph flows in from the periphery, and then in this subcapsular lymph sinus, then it gets filtered through the dense aggregation of lymphocytes, cortical sinuses, then gets into the medulla. Sinus here means a empty gap, a gap looking space, wider than a blood vessel or a capillary.